can't cut it. There's pipe.
Okay.
Happy birthday.
Happy birthday. Is your birthday?
Happy birthday.
Happy birthday. Okay, so we'll continue on. We went over that video yesterday on electric potential. Let me just remind you. I posted the video for yesterday, and I linked the video that we watched in the description. So it's there on electric potential. So electric potential, symbol for that is V, units of volts. It's a little confusing, but I'll put the units. Okay, it is defined as I'm just talking absolute value here, that change in electric potential energy a little E here. Divided by Q. It's the potential energy per unit charge. Okay, now, what is that change in potential energy? It is, for electricity, it's this. It's very similar. And yes, the negative is taken into account. When you're calculating this, you have to include sign. So if they're opposite charges, this expression, which looks like it's very similar to this, it's similar to the gravitational energy, gravitational potential energy, okay, which is negative. Well, the negative comes into play when we have opposite charges, so it is there implicitly. So that's this. That is this. And yes, you don't have the math skills to derive it. It's derived in a similar way that we derive this using calculus. So that is the potential energy. And then we have to remember to divide it by small. What's small q? Big Q is the source. Small q is what's being acted on. It's not even needed to do the calculation for electric potential. So electric potential just reduces to this, KQR. And it is related to something in the real world. If you have two terminals of a battery, that's one terminal. Don't laugh. That's my battery, my car battery. Okay, so I don't know. This is the positive. This is the negative. These are called terminals. Terminals meaning that you can connect your wires to it. This here would have an electric potential of that. So that would be my VA. That'd be terminal A, that's terminal B. VB, let's see, it's 24. VB would have to be negative. These numbers aren't right, but I don't know. Negative 10 volts. Okay, the difference VAB, the VA minus VB. That's 24 minus a negative. So that works out to be 34. That's not the actual voltage of a battery, but the idea is right. This is a battery in a car. Okay, so that's how your electric potential relates to real life. It is the difference between the potentials of these terminals is what we call voltage. This is voltage. It's also known as potential difference or difference in the potentials. Okay, so it's just, whoa. Yeah.
How do you know if you should do VA or
It gets a little bit confusing, I agree. Yeah, I wouldn't, most of the time we deal with the absolute values, so it really doesn't matter the order. Yeah. But the problems that we do 95% of the time, the order doesn't matter. And if you do it the wrong way, you'll be able to make sense of it. And I'll tell you the context in detail later, but usually you'll use this in terms of trying to find potential energy in order to calculate the kinetic energy. And you'll know that the change in kinetic energy, because it's picking up speed, has to be positive. So you'll just force the change in potential energy to be negative. So remember this equation here? We're going to make use of it. This will make more sense later, but for example, you'll know this has to turn out to be positive, so you'll force this to be negative. If you turn out to get a positive answer, you say, well, it has to be negative to make sense of the equation. So yeah, don't get too concerned about that. You'll be able to make sense of it in terms of the sign, in terms of the context of the question. Okay, so we're just going to rearrange this. I'm not going to use it yet, but oh, squiggly. Put the Q in front. That's equal to change in potential energy. Okay. What else is change in potential energy? It's equal to the work done. Okay, so all of this is related. Anyways, don't want to get too hung up on it. Okay, let's go through an example problem. Example 1. This is just calculating the potential. We want to focus on that. I want to be more exact so it doesn't confuse you. Let's just change something here. Sorry about that, because this will be confusing. I've seen it done both ways, but let's just take the triangle out. This will make more sense to you later. Take the triangle out. And then we'll come back to this later. This will make more sense later. Okay, example 1. Calculate the potential. I just started. Calculate the potential at point P. Given the following diagram. Do you need me to go back? Is that what you need? Or?
no, it's just asking that you didn't put the sign of the triangle on T.
I just removed the triangle for greater clarity later on. I'll come back to it. Otherwise, you're going to get confused. So, calculate the potential point P given the following diagram. So let's look at this. It's positive. If you don't see any sign in front of it, it means it's just positive. This is a diagonal. This is 4 microcoulombs. It's positive. Sure. That's 7. That is 5. We better. It's 3. Okay, it's 3 microcoulombs. I'm going to label these as well. So that's my Q. That's my Q1. That's my Q2. That's my Q3. Really doesn't matter. Sometimes they'll put this in here, but it really doesn't matter what the angles are. You need to know, obviously, that it forms a right angle. That's all you need to know. Actually, you don't even need to know that. What's important in this calculation is the distance and the charge. That's it. It's a scalar. So you're going to find in this question V total. That's what you're after. And V total is going to be equal to V1 plus V2 plus V3, taking into account that this is negative. You're going to insert the negative in there. It'll end up subtracting. Okay, so we need to calculate each of the electric potentials. This is K Q1 over R1. This is R1 here. Okay, so it's 3 microcoulombs, so it's 3 times 10 to the minus 6. And then the distance is 5 centimeters. We've got to convert that to meters. So that works out to be 5.4. Volts. It's volts. Or joules per coulomb. You've got to be aware of both. We usually use volts. Over R2. R2 is this. This is R2 here. That's R2. 7 centimeters. That's 4 microcoulombs. Micro meaning that little u is 10 to the minus 6. And the distance is 7 or 0.07 meters. I'll carry an extra digit with this one times 10 to the 5. volts. V3 is KQ3 over R3. Subscripts all the same. This is R3 here. It's 5 centimeters. It's the same calc, is it? No, it's a different charge. Okay. So 9 times 10 to the 9 times, make sure you include, now we include a negative. When you're calculating electric potential, you have to include negatives. Has to come out at least in the final answer. The distance is 5. This works out to be negative 3.6. volts. V total is this here again. Get your V total. Taking into account, again, this is negative. Oh, that's negative. Okay, so just add up the numbers. You've got 5.4. They're all 10 to the 5, so I'll add that subscript or that exponent in later. 5.4 plus 5.14, that's about 5.5, minus 3.6, that's about 10.5, minus 3.6, it's about 7. Works out to be 6.9. Now we can re-add the exponent in 10 to the 5. Volts or joules per coulomb? Okay, notice it's positive. It ended up, yes, we had to subtract this last term here, but the overall total is positive. So that means, what does that mean in terms of a point? It means if I were to take a, let's say, a proton, and I were to push it towards point P, it's positive. This, I can do the calculation out here. It would be positive as well. Okay. If you were to bring this actual proton all the way from infinity, so distance really far out there, all the way to point P, you would do positive work. That's what it means. Bringing this from a point really far away to point P, you'd have to do positive work. You have to exert a force to get it to move to point P. If it was an overall negative value, if V total ended up to be negative, you could just let the proton go and it would float towards point P. Kind of like letting a brick go. It would fall. That's what it means. Example 2. Yeah.
Sorry, could you go back up to the,
Yeah.
when I put that into my calculator, I get a different number. I get this.
Oh, did I? You know what I did here with V3? That's, sorry, my mistake. This is 2. That should be 2. That's how I got that. Then it works out. Yeah.
Like in most cases, always given that this particular free charge is durable, you found the right angle.
Yeah, you'll be given 2 or 3 charges and you'll be asked to solve for the total. You have, what you need to know, here's the key point, what you need to know to calculate the electric potential is the distance from the charge to the point. That's what you'll be given as well. The angles are irrelevant. You just need the distance from the charge to the point. Yeah. Okay. Okay, example 2. Let's write this one down. How much work is done against an electric field By the way, I only got 2 hours sleep, so don't have high expectations with me today. Electric field produced by 2.5 microcoulomb charge. Object. When a 0.025 microcoulomb charge is moved from 3 to 1 centimeters. Okay, so I'll show you visually what's going on. Okay, remember this, work is going to be equal to Q, V, we're going to get a little bit more exact, we're going to add this subscript, VBA, the difference, or VBA is the difference between electric potentials. Okay, so I'll show you what this refers to in the diagram. So you've got a charge and 2.5. This is your Q, big Q. It's important you get this right. Upper and lowercase. That's 2.5. That's stationary. That just sits there. You're moving a smaller charge from point A to point B. Now, you're used to calling these initial and final positions. It's the same thing. You could refer to it as initial and final. You'll find most textbooks use A and B. Okay, so you're moving this charge, and this is small charge. It's important you distinguish between upper and lowercase. It's a small charge, 0.025 microcoulombs. It is positive. Okay, that's positive. It's important you understand that. If they're both positive, they're going to repel each other. So to get this charge from A to B, you'll have to do work. You have to force it to happen. It's kind of like lifting a brick above the ground. You lift it from, let's say, where this table surface is to a meter above it. You have to force that to happen. You have to do positive work. You're going from this is a lower potential to a higher potential. Just like you are when you're lifting a brick. This is lower potential to higher potential. So positive work is done. Okay, this position here has a VA. This position B has a VB. Both of them have electric potentials. This electric potential is higher than VA. VA is a lower potential because it's farther away. So what do we need to calculate the work? We need, this is the shorthand way of writing it. This is the full version of it. Okay. So what do we need to calculate the work? We have the small q. We have the small q. What we need now to calculate are VA and VB. Okay. What is the electric potential at A? What's it given by? This. You use the big Q, not the small q, to calculate electric potential. Which big? It's this Q here. It's the only big Q. That's the one you're going to use. This should be RA. What's RA? RA is the distance from big Q that's your RA. That distance. Okay. We're told, what is that distance? It says in what I just stated that this small charge is moved from 3 to 1 centimeters. So this is 3 centimeters. Okay, so we can do that calculation. And convert the meters to, or centimeters to meters. So that works out to be 7.5 times 10 to the 3, 10 to the 5, pardon me, volts. Okay, VB, that's the potential at this spot here. We need to know the distance from big charge to that point B. What's that distance? We're told it's 1 centimeter. One centimeter. That's my RB. My RB there. I'm sorry, guys, if I'm a little off. Literally, I didn't get much sleep at all. Okay, so big Q is the same. That's the source of the electric potential. Same as above. What changes? The distance. You're going from 3 to 1 centimeter. I think this is, you want to double check this. I'm pretty sure this is correct. 2.25 times 10 to the 6. What's the unit for electric potential? Unit is volts. Yeah. Okay, work. What's work equal to? Q times, we got to be specific now. Now we're getting more exact. It's Q times this here. What's this called? This is called the potential difference. Or change in potential sometimes. Most textbooks refer to it as potential difference. That's the proper term. So the work done is equal to the small q. The small q is the charge that's moving. Charge that moves. That you're doing work on. Times the potential difference. What? 2.5 times, yeah, 10 to the negative 8. Okay, so just so you're clear, 0.025 microcoulombs is the same thing as 0.025 times 10 to the minus 6, which is the same thing as 2.5 times 10 to the minus 2 times 10 to the minus 6, which is where I got 10 to the minus 8. Times what? Times the potential difference, what we just calculated here, or VBA. This is VB minus VA. I need more room, but .5 times 10 to the minus 8. Just plug in your difference. VB is 2.25. And VA is 7.5. And that works out to be, I'm just going to give you the value. You tell me, is it positive or negative? And what's the unit? Is it positive work? Yeah, think in terms of what you're doing. You're pushing a small positive charge towards a bigger positive charge. Is that positive work to do that, or does it just naturally? If it's positive work, it means you have to force it to happen. Okay? If it happens naturally, where you let the positive charge go and it just floats towards the other positive charge, that would be negative work. So which is it, positive or negative work? Yeah, it's positive. Yeah, and it works out. That's bigger than that. What's the unit for work? Yeah, good, because it's related to potential energy. Okay. Now I need to do one more lesson on electric field, and we're done electricity. And then you can work on problems. Okay. Electric field between parallel plates. Yeah, sorry guys if I'm a little cranky today. I don't know why I did it. I worked out at 11 o'clock at night and I couldn't sleep. Yeah, I know. That was dumb. Whatever. Okay. No one cares anymore. What are parallel plates? This is, first of all, I'm going to refer to this a lot. What we've been working with are point charges. This is a point charge. Anything like a proton or an electron or an ion, like a helium ion, right? Point charges. We know what the electric potential, in that case, the electric potential is this. That's the electric potential. Okay, you can only use this expression for point charges. When you're dealing with parallel plates, and you'll be able to see it in a diagram, in the problems you'll get, you'll have diagrams with plates. These are, in fact, what are these? These are just rows of positive point charges. That's all this is. So what is each? That's all these are. These are kind of like protons lined up. I'm going to have to erase some of this because it'll get confusing if I don't. But what do the rays coming out? What do the field lines look like coming out of each of these? Looks like this. Oh. That's the first field line. Okay. What about, I'm going to look at this proton over here. What about this field line here? Field lines like that. I don't want to get too much into it, but you have a field line here pointed that way. You have a field line here pointed that way. Both of them, if we zero in on this, both of them have x components. I need to make this more narrow. This ray here has an x component that points towards the left. And this ray here has an x component that points towards the right. So these, what happened? Why are these lines here, man? Oh, I know why. Because it's a line page. Okay. That's an EX minus, that's an EX positive. Okay, these are just numbers. So this could be positive 5 newtons per coulomb. This would be negative 5. You can actually calculate these values. Okay. The point is that these x components are in opposite directions to each other. They will cancel each other out. There is no x component. What will you end up with? You'll only end up with y components. These two y components are pointed in the same direction. They will add with each other. So what's my point? My point is you'll end up with inside two parallel plates, you'll end up with a field looking like this. This is my whole point. You have a line of positive charges here, which are just protons upon protons. And on the bottom, you have a line of electrons here. Negative, 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 negative. Okay, you'll need equal amounts on top and bottom. The x components, like I just said here, these x components, that one and that one, cancel each other out. You'll only end up with y components. How does that translate in this diagram to look like this? You'll get field lines that look, well, I'll do it in yellow to be consistent. You'll end up with field lines that look like this. Okay? That's all you're left with. The x components cancel out. You just drop railroad tracks, parallel lines. See if I can get lazy here. Will this work? Kind of lazy. It doesn't quite work. Okay, you end up with parallel lines pointing down, away from the positive. Field lines, electric field lines always point away from the positive and towards the negative. Why is that important? Because what we're used to dealing with is field lines that look like this. You got a positive charge. We're used to looking at field lines that are diverging. This is a point charge. Field lines spread out like rays of the sun. And yes, they point away. They point away. Point away. They point away. That's a point charge. The field is given by this. That's the electric field. The electric potential is given by this. Notice what's similar. What's similar in both is there's an R, in this case an R squared, in this case there's an R in the denominator. What does that refer to? That refers to the fact that the field As you move farther and farther and farther and farther away, the field gets weaker. That's why we have r and r squared in the denominators. Okay? What about these parallel plates? By the way, these parallel plates are used throughout your circuitry in your iPhones and your computers. They're used in what's called capacitors. So this is foundational to electricity. It stores charge. It acts like a temporary battery. In fact, this is what we're going to be turning to in the future instead of batteries. They're already using, I think Tesla's testing them. Check it out, capacitor. It stores electricity. That's what it's being used for. Anyways, what is my point of drawing this first? My point is, so you're clear on something. Look at the field lines here. Look at how they're parallel. They are not diverging. They are not spreading out like rays of the sun. Spreading out means it gets weaker and weaker and weaker the farther away you get. Just like sun rays. The farther you get away from the sun, the weaker the sunlight is on the surface of the planet. Mars creates or receives less heat than the Earth does. In this case, they don't diverge. It's constant throughout. They're parallel, which means the electric field here, let's say, I'm just making up a number. Let's say the electric field is 10 newtons per coulomb. At this point here, the electric field is 10 newtons per coulomb. Doesn't change, it's constant. Electric field is constant. Not so here. You can see from the equation, the farther you get out, the less the field. So if I were to put numbers here, this could be, at this point here, it could be 20 newtons per coulomb for the electric field. We'll call this is the initial, or E1. And out here, let's call this E2. E2 would be less, 5 newtons per coulomb. And the farther out you go, the smaller the number is. Not so here. Number is constant. Electric field is constant. Why is that important? The force needed, let's say you had a little charge here. Say you had a positive charge, a proton, and you're moving that proton. You're moving it against the field, kind of like lifting a brick. Because the electric field is constant, the force that you apply would be just equal to QE. That force is constant. That force is constant. That makes it easier for us. Okay? So I'm going to derive some equations for you, keeping all of that, or taking all of that into account. So when you're doing, let's say, I'm going to copy this all out again and erase it. I'm going to need it again. Okay. Let's say you've got the same charge, the proton. You're moving it up. Let's say you move it from the bottom of the plates to the top of the plates, and that distance is d. What's the work done? Well, work is just, if it's a constant force, the work done is just force times the distance. So we want to calculate the work to move it from, we'll call this point A, the bottom where the plates are, to point B, the top of the plates. What's the work in order to go from A to B? It's just the force times the distance, D. between the plates. What's the force equal to in terms of the electric field? QE. Remember that equation? Electric field is just force divided by charge. So you rearrange, you get QE is equal to F. That's the definition of electric field. Okay. What is work also equal to in terms of potential energy? When you lift, how is work related to potential energy when you lift a brick? What's work equal to? If I go from here to here, work is equal to the, work is also equal to, yeah, but in terms of potential energy, how does it relate? Yeah, change. So these two are equal. Those two sides, the right sides are equal. Now, in what we like to do is relate, we like to relate potential difference to the electric field. We want to relate potential difference. How is it related to, I know it's proportional. In what way though? What's the equation? That's why we're doing this. The change in potential energy, when you go from A to B, there's an electric potential here at point A. There's an electric potential here at point B. The change in potential is just Q, V, B, A, where VBA is the potential difference. Okay, what cancels out? There's a Q on both sides. Small q, doesn't matter, don't need it. So you get VBA is equal to ED. Rearrange it. This is the way we usually write it. That's your equation. That relates what? That relates the constant electric field between the plates to what? The potential difference between the plates, between the bottom plate and top plate. So these are actual values. So VB might be 300 volts, and VA might be 100 volts, positive each. What's VBA? VBA is just VB. Take the first subscript and subtract from that the second subscript. So in this case, it would be 300 minus 100. 200 volts. Let's say the distance is 5 centimeters. So VBA is 200 volts. 5 centimeters, convert it to meters. So what's 5 goes into 40? I'm guessing. Is it 4,000? Is it 40,000 or it's 5 goes into 200? Yeah, 40 times. I think that's right. What's the unit? Newtons per coulomb, or what's the unit here? The unit here is volts. So the alternative is volts. The unit on the bottom is meters. This becomes an alternative unit for electric field, volts per meter. Okay. Notice something. Go back to what I wrote earlier. Look at this box here. This is, again, the equation for the electric field. In what state, in what context? Parallel plates, capacitor. That's the equation. You do not use this equation. Notice how there's a difference. KQ over R squared is not the same thing as volts divided by distance, or potential difference divided by distance. Two different equations. When do you use this one? When you have rays diverging out from the charge. In other words, when you have a point charge. Different equation. This is the equation for point charge. And this is the equation for parallel plates. Parallel charged plates, obviously. Okay. Couple things, one more thing before I go on. Make another copy of this. Let's take this proton. See this proton here? I'm going to erase it. Erase, man. Go. Yeah, I don't know what the distance is. We can deal with that later. Let's put it up on top now. Let's say we start the proton on top here. Well, that's kind of big. I want to move it right to the top. Come on. Okay, that's my proton. I push it up to the top. It's right at the top. I let it go. What do you think it's going to do? Go down. That's similar to what in the gravitational case? What example would you use? Yeah, let's deal with the simple case of near the surface here. What example would you use compared to the proton falling towards the negative plates? Yeah, brick falling. Brick's up here, falls. Brick, if it's gravity, the brick is at a higher potential here. Do you agree? Lower potential here. So similar for the proton. This is a high potential. And it's going to move all the way down here. It's going to reach bottom plates. This is lower potential. So the proton goes from high to low. If it's going to move naturally, it's going to move from a high to a low potential, just like a brick does. Just let it go, moves naturally. You don't have to do work. What equation, if I gave you a brick of mass m, it falls from, I gave you the height, whatever the height is, and you were asked to calculate the speed of that brick before it hits the ground, what equation would come to mind? What law would come to mind? I let an object go, it just falls. And you were asked, calculate the speed. You could use kinematics, but what other equation could you use? That relates to potential energy. You let the brick go. Well, I'm telling you, let's say you have a potential energy up here. How does that relate to the speed of the brick down here?
That equals kinetic energy.
Yeah, so what's that law? What's a law that relates kinetic to potential energy? Very good. It's this. Some of you have been writing it differently, but it's essentially this. What we worked with in the case of the satellites. That's This equation is a conservation of energy. This is what you would use for what? If the question was, what's the final speed here? Okay, or what's the kinetic energy? Either question. What's the final speed or kinetic energy of this proton as it falls? You would relate its initial speed, which in this case is 0, but it doesn't necessarily have to be 0. It is in this case. You relate the initial to the final in terms of this equation here. Okay? So let's write it out. What we're after is the final speed, an equation that relates the final speed to the potential difference, VB minus VA. That's what I'm after. Relate VF to VBA. VBA, this is not a speed. This is, VBA is potential difference. Okay, kinetic energy. What does triangle mean? It means final minus initial. Oh man, I made this too small. Okay, I'll write it over here. Final minus initial. What's the initial speed for this proton at the top? If I let it go from rest. Yeah, it's like a brick. Letting a brick go from rest. Initial is 0. This whole 0 times anything is 0. That's 0. That's the left side of this. It's the right side. Negative. What's the change in potential energy? What's that in terms of the potential difference? It's QVBA. This, I'll write it over here. QVBA, that's 2. QVBA is change in potential energy for the electric case. That's always true. It doesn't matter whether you're dealing with point charges or parallel plates. That's always true. So I would write it. Oh. And this VBA is just what? VB minus VA, which you'll be given. You'll be given the electric potentials. If you're not given that, if you're given the electric field, then you've got to go back to our equation earlier. Go back to this one here. VBA is equal to the electric field times the distance between the plates. So an alternative, it depends what you're given. If you're given the potential differences, then you use this equation. If you're given the electric field, remember it's equal to change in potential, sorry. This here is this here, it's just equal to that. You just replace the VBA with this. That's it. Now, I get the question, well, there's a negative sign here. This is positive. Isn't that positive? Isn't that positive? Doesn't it turn out to be negative? No, this is positive. That you know with certainty. Kinetic energy is always positive. Force this to be positive. Don't worry about the details. Just force the right side to be the same sign as the left. I mean, I could go into details as why it's negative, but don't worry about it. Just force the right side to be the same size or sign as the left side. Yeah, I mean, like I could get all these details and that, but then it's just like waste time. So just that kinetic energy has to be positive and that it's equal to the right side, so the right side must be positive. Simple as that. Let's now do a problem in regards to the parallel plates and an electron that drops, similar to the proton. I'll draw it for you and everything. So this is example. This is really the first example. We did an example of calculation. Yeah, I'm going to skip to the harder one. So this is an electron is accelerated from rest through, pay attention to what the words say, through a potential difference. You need to be aware. What is that? That's your VBA. They won't tell you that, but that's what VBA is. It's potential difference of 30,000 volts. What's the kinetic energy gained by the electrons? Now they could have asked you what's the speed. This is even easier. So what's the kinetic energy? Let's do that first. And then we can talk about the speed, the kinetic energy gained by the electrons. Okay? So I'll draw it visually as far as what's happening. It's basically this, what I just drew here. Okay? I have to do a little bit of changing here, but it's similar to the proton falling, except what they've done is they've reversed everything. So this would be make sure I finish this first before you draw anything. They reverse the plates, basically. Negative here, positive here. Okay. Here's the confusing thing. Direction of the field is up. It's always in the direction that a positive charge would move. Field is up. That's the direction a positive charge would move. Okay, now zero in on this. This now becomes a negative charge. What does a negative charge want to do? A negative charge wants to move away from the negative plate and towards the positive plate. It's very similar to the previous case of the positive proton falling. What's the higher potential now? For the electron, the high potential is at the top again, where it starts, just like the brick. Higher potential is at the top. Lower potential is at the bottom when it reaches the positive plates. It's falling. It's analogous or similar to a falling brick. So in order to find the kinetic energy, the equation that should come to mind is what we just used. Where this here is just QVBA. And your kinetic energy that's gained this is it. That's how much it's gained, because the initial is 0. And you don't even have to calculate. You could calculate the speed if you wanted to, but whatever the right side is equal to, that's your kinetic energy. So let's calculate it. What's the electron? One, I know it's negative. I'm just going to use absolute value. You can look it up in your data booklet or data table. It's 1.6 times 10 negative 19. It's the elementary charge. Your VBA is given. It's 30,000. So this works out to be 4.8 times 10 to the negative 15 joules. What's the sign? I mean, yes, there's a negative here, but don't worry about how it disappears. I know that kinetic energy is always positive. This must be positive. It gains kinetic energy. In this case, it gains kinetic energy, so it must be positive. It's like a falling brick. When a brick falls, just before it hits the ground, it's gained kinetic energy. Whatever the left side is in terms of sign, just force the right side to be the same sign. In this case, positive. Okay, so on your try, you can work on this now. What time is it? Yeah, this will be your homework. I'm going to give you something else to work on as well. So page 286 to 287, 1 to 6, and then 8. Okay, and then on page 294, to 295, 1 to 6, and yeah, space is electric if the parents are and have a potential to restrain well, how much work is done. Oh, okay. You know what? Let's do in this case 1 to 8. Let's do just 1 to 8. Skip number 7 in the first, and this skip 7 here, but do all 8 in the second set of questions. Please tell me that I remembered to record. I did. I did record it. I have, that's quite a lot. I need to push ahead though. One section in the new handout. You can read. It's a bit to do tonight, but yeah. It'll be, I see you Tuesday and Monday's off. Tuesday, I'm thinking of maybe making it Wednesday, but I'll let you know tomorrow. Okay, on this handout here, you can read it. It's pretty actually simple. Just plug and chug. You ever heard that before? Yeah. You can just do page 352, 1 and 2. You can read the previous, on that new handout. Well, it's homework. You can, do you want me to make it an assignment? Page 352, 1 and 2. You have to read what comes previously, though. I'll give it to you. I don't even know what all that's. I don't even know what you guys look like. It's not good. I think I just made an exact amount of profit. I think you need to give me a printing lesson. Got it? Okay. If I fall asleep in the seat, just don't wake me up.
Mr. Killian, when do you think you'll get a test back?
I'll probably get through most of it tonight, but I'm not guaranteeing
No,
it.
please take your time. Please don't.
Okay.
Right now,
Think about it, Monday's off, so.
You think I should, I don't know. I do. No questions. Got a question? I'll post this video tonight. This is a stop recording.